Hello. In this knowledge clip, we discuss utility functions and the general concept of utility. Why would consumers demand a certain good? Economics answers by stating that because consumers have a certain need, some goods are going to be sought after because they have the capability to satisfy those needs. By consuming such goods, you can increase your benefit. The total benefit is also referred to utility when, in economics, we discuss individual consumer decisions. Utility is hence the total benefit that you gain from consuming a certain amount of a good. The mathematical representation of utility, and also that of tastes and preferences, is referred to as the utility function. Now I denote this concept by u, and as you can see, I did not define a functional form here. I just call this function f, and you can see that it depends on the quantity of the good consumed, denoted by q. A related concept is the marginal utility, denoted here as mu. This is going to show us what happens to the utility if we increase the consumption by an additional unit. Or, if you already have the function, then you can also define this marginal utility as the first derivative of the utility function with respect to the quantity of the good consumed. Now, let us visualize utility and marginal utility as a function of the quantity consumed. We are going to assume that we have a certain good, for example, water. So, if you are thirsty, then the first glass of water is going to increase your utility quite much. That is, the first step in the utility function is going to be something like this. That is, increasing q, increase u, so we have also a marginal utility of the same size. If you drink another glass of water, it's also going to add to your utility, but the addition is going to be somewhat less than before. This is what we refer to the law of diminishing marginal utility. This is a psychological observation, namely that the effect on utility of a good is decreasing as you increase the consumption of the particular good. A third glass of water may still increase your utility, but you can see that this increment is going to be quite close to zero. Up to this point, we can say that water was a good, because it had a positive marginal utility, even though it was diminishing. And this is the point, what we call saturation, when the marginal utility is basically zero, where any agent who can make a decision freely about consumption would arrive. Even if the good was absolutely costless, even then individuals would not be willing to go beyond the point of saturation. And there's the reason that only this part of the utility function, with the positive marginal utility, is really relevant for our model of the consumer's decision. But for this introductory clip, let's assume that the consumer may actually be forced to consume beyond the point of saturation. If some evil agent forces the consumer to drink another glass of water, this is going to cause a discomfort. That is, it's going to reduce utility, so we have a negative marginal utility. Consuming another glass of water will do even more harm, and the marginal utility will be negative, but higher in absolute terms. So, This is the point when we cannot really call the water a good anymore because it doesn't do any good. We refer to it as bad or harmful good. So altogether, here we found that initially we have a nice positive sloping utility function with a positive but diminishing marginal utility function, but after the point of saturation we have a new part of the utility function where we have a negative marginal utility. As such, at this point of saturation, or after the point of saturation, we cannot really call a particular product a good anymore, because it's bad. Theoretically, hence, we find that the relationship between utility and the quantity consumed is not monotonic. First it's increasing, then we may imagine that it is decreasing. Yet, as I told you, because voluntarily no agent would consume beyond the point of saturation, the first blue part is going to be relevant to us, and that's why, in practice, we are going to model the utility as always having a positive marginal utility at most. At high Q, we assume that it is very close to zero. Let us look at some consequences of the low diminishing marginal utility. So, in this course, and usually in economics, when we discuss consumer choice, we are going to assume a positive but decreasing marginal utility with some exceptions. Mathematically, these two assumptions, namely that marginal utility is always positive but diminishing as Q, the quantity consumed of a good increases, means that whatever utility function we choose, it should be concave. Concavity is a mathematical concept that you possibly already heard of, but maybe you have forgotten it. So let us refresh it. If I have concave utilities, then if I depict the total utility as a function of the quantity consumed, I will find that if I take any 2 points along this utility function and I connect them with a line, then all points of this line in between the 2 points is going to be below the function itself. This is what we call concave, and here what I'm showing you is going to be just the opposite, a convex function. So a convex function could not be a good utility function, but a concave one would. Let us see an example of a concave utility function, the logarithmic utility. Here, u is defined as a, just a scalar or a constant, times the natural logarithm of q plus 1. You may ask yourself why it is not just simply the logarithm of q. Why do I add a 1 to the quantity consumed? The reason is that logarithm of 0 is a not defined point of the function. So we cannot really assign any value to the logarithm of 0. So if we would like to look at the total utility when no unit of the good is consumed, then it is best to just simply give add to the quantity. That is, know if q equals 0, then the logarithm of 0 plus 1 is going to be the logarithm of 1, which is equal to 0. So by adding this extra 1, we actually shift the function so that it starts from the origin. Let's look at the marginal utility of such utility function. In this case, we take the first difference of the utility function with respect to q, and using the rule that you can see here below the result is going to give us then that the marginal utility will depend on the actual consumption, and it will be equal to A over 1 plus Q. But because Q can be 0 or a positive number, and A is assumed to be positive, we know that the marginal utility, if you choose such a logarithmic function, will always be positive, hence this fulfills our assumption. Second, the concavity. If you take the first derivative of the marginal utility, or in other words, the second derivative of the utility function with respect to q, then you are going to get a negative number. Using the rule of the first derivative of 1 over x, actually we can express the second derivative as minus a over 1 plus q squared. And because a was positive and 1 plus q squared is always positive, and we have a minus sign there, it is guaranteed that the second derivative of this function will always be negative, and this is the definition of concavity. The first derivative is positive and the negative, and the second derivative is negative. So far, I assumed that utility can only be improved by increasing the consumption of a single good. This is of course highly unrealistic. In practice, consumers have a multitude of goods which could be consumed or substituted for each other. In order to capture this complexity of the real life, we are going to use utility functions with two possible goods. Now, you may say that even a utility function with only two goods is going to be far too simple. Yet, you can always think of one of the goods as the combination of all other goods, and then basically, by using at least two goods, you can generalize the decision process. Also, even having only two goods like this is going to be very difficult to depict graphically. So, the point is that even if we use two goods in our utility function, we will still be subject to the same assumptions as before, namely a positive marginal utility, which is diminishing. So we will still need a concave function. One example could be just simply to add up two single good logarithmic utility functions, because utility functions are very often quasi-linear. No, without really going into that concept, basically that means that you can write these two functions as a sum and you are going to get a still valid utility function. So, in this case, I have a utility function for which I can calculate the marginal utility, but this time with respect to two goods, because utility may be increased by consuming more of x and also by consuming more of y. Taking the first derivative of this function is going to give us a over x plus 1 just like before, and b over y plus 1, which both are going to be positive. The problem is, however, that even if you limit the number of goods to 2, you're still going to have a 3-dimensional problem. And you should use some computer, like I did, to arrive at a graphical depiction, a 3-dimensional surface. But even this would be extremely difficult to work with. Instead, we are going to try to find a visualization method which makes our life much simpler and reduces the problem from 3 dimensions to 2 dimensions. So how could we do this conversion to 2 dimensions? First, we are going to get rid of one of the variables, and the variable we get rid of is actually the total utility. So the trick is to have an implicit visualization of this function. So we are going to take the utility function and we fix the utility at a certain level. And then what we are going to depict is all those combinations of the two goods, or in other words, all those bundles or baskets that the consumer may choose, which give you exactly the same level of utility. For example, if I take the previous slide's utility function and I assume that A and B are both 1, and I assign a value of 2 to the total utility, I can write the utility function as you can see in the first row. Now all I have to do in order to get a formula for the curve is to express y. And doing that, I'm going to get a certain functional form. Here I find that y should be equal to the exponential of 2 minus the logarithm of x plus 1, and I should subtract 1. No, this is going to be a two-dimensionally visualizable function because here y depends only on a single variable x. Because any combinations of y and x are going to give you exactly the same utility as long as they are along the same curve, we call such a curve an indifference curve. Indifference refers to the fact that the consumer will not really care whether it consumes one point along this indifference curve or a different point. That is, all these points are going to be the same for the consumer. I depicted indifference curves for two cases here, when the total utility is 2 and when the total utility is 3. You can see that these are going to be parallel to each other and the indifference curves are negatively sloped. Also, you can already see that the indifference curves are inward bowing, that is, they are convex. If you have a concave utility function, then the indifference curve is supposed to be convex. So there are certain behavior, certain features that we expect that a so-called well-behaving indifference curve is going to have. So these so-called well-behaving indifference curves are those indifference curves which are usually depicting the relationship between standard goods. There are of course goods with some very special relationship, and for them we have to use non-well-behaving indifference curves, but we are going to discuss those special cases a bit later. So a well-behaving indifference curve should be negatively sloped, and this is because of the positive marginal utility of both goods. This is very easy to understand. Now, along the same indifference curve, we know that utility remains the same. Now, this is not possible if, by increasing x, I could also increase y, because then, obviously, I would consume more of both goods, so this should then give me a higher utility. That is, if I want to fix utility along the same indifference curve, when I consume more of x, it's necessary that I have to reduce my consumption of y, and this gives us a negative slope. The second one is this inward bowing or convexity. This is due to the diminishing marginal utility. That is, if you already have a large amount of y, then its marginal utility will be much lower than that of x. So when you have y in abundance, then you will be willing to give up a relatively high quantity of y in order to gain a smaller quantity, extra quantity of x. And this is going to give this inward bowing characteristics to the indifference curve. So here we find that the indifference curve should be convex. That is, if we connect 2 points along the same indifference curve, then in between these 2 points, the line is always above the value of the function itself. And as we already saw, we will always find that indifference curves lying to the right of the original indifference curve are going to represent a higher utility level. And finally, it's important that indifference curves are parallel. That is, they cannot intersect. This means that it is not possible that a single combination of x and y would have 2 different utility levels. So as long as the preferences of the consumer are consistent, indifference curves cannot cross. And also, it's important to note that indifference curves are monotonic. This means that that cannot really curve back. So when you have a well-behaving indifference curve, then it should always have a negative slope. It cannot somehow just turn back and have a positive slope.